Chapter 4 on gravity. So we need to be able to, hang on, a bit of glare there. Oh, I haven't got my glasses on now, so I can't read. Yeah. Righto. Recall Newton's law of universal gravitation. Solve problems. Define the terms. Solve problems involving gravitational field strength at a distance from an object. All good. Righto. And there's our formulas that we need to know. Nothing too difficult or special about those. So where we've used F equals ma, this would be F equals mg, g being the acceleration due to gravity. All right, let's have a quick look. All right, so gravity is a natural phenomenon by which all things which have mass are attracted to one another. And there's a challenge here, which is greater, the Earth's pull on the sun or the sun's pull on Earth. It's one of those action-reaction type of things. So A pulls on B and B pulls on A with the same force, just like in electrostatics when we get to that. All right, so this is Newton's law. So the force from gravity is directly proportional to the product of the two masses. That's the two masses there. G is a gravitational constant and inversely proportional to r squared. So it's 1 over r squared. So if we were to graph this, and we have force on the y-axis and mass on the x-axis, it's directly proportional. So you're going to see a straight line. If you were looking at force on the y and r, the distance between the two centres, there's a diagram down here, you measure from the centres, you would have this parabolic curve, and to get it into a straight line, you would have to graph FG against 1 over r squared to linearise the data. All right, so the big G, capital G, is constant, gravitation constant. There's its value there, 6.67 by 10 to the negative 11 newtons metres squared per kilogram squared. So we need to be working in metres and kilograms. So as I said before, it's a force between the two. This one will attract that one, and that one will attract that one, and the force will be the same. So just like the Earth attracts you, you attract the Earth. It's just because the Earth has such a huge mass in comparison that we don't really see an effect on the Earth. And your mass is small in comparison, so we do see an effect on you. Right, this attractive force always points inwards, so it's between the two objects. They're two equal and opposite forces. It is a vector quantity and it has both magnitude and direction. The law applies to all objects with mass, big or small. And if you've got two big objects, you just treat them like point masses. So we're using the centre of the masses. Separation distance, as I said, has to be in metres. And you'll be squaring it. And then it's just straight substitution in. Righto, this one has just got 72 kilogram physics student in an aeroplane 10,000 metres above the Earth's surface. Remember, you measure to the centre, so you also need the radius of the Earth and add it on. So it's just an add, and then it just goes into the formula again. It's not very difficult. Righto. So this was an experiment done by a guy called Cavendish, Henry Cavendish. And he hung it down, he had his little masses here, and then he would bring another mass in close. And the same sort of, I think it's called a torsion bar, was used in electrostatics experiments. You can get very small forces to cause a degree of motion there. So they were able to show that force was there, and these are those graphs I was talking about. So if you look at force against distance, you will get this shape. So to linearize it, you put it 1 over r squared. All right, now if you think about the formula, force, the slope of this, you'd have force divided by 1 over r squared, which is force times r squared. And when you take into account the masses, so fr squared, g times m, that would be the slope. Divide it by the 2 masses used in the experiment, and that enabled them to get a value for big G. Right, so that calculation and that experiment has been done thousands of times. They've got here, so for this set of data, they've worked out the absolute error and the percentage error. Remember, that's a comparison to the known value. So in this one, this experimental value, 6.63, the accepted value is 6.67. So you need the difference between the two of them. Divide it by the accepted value, multiply by 100. So 0.6%. If you got that as your results, you'd be very excited. All right, gravitational fields. Just like the fields you may have seen with magnets when you were younger, gravitational field is a region of space surrounding a body in which another body experiences a force of gravitational acceleration. And we draw them like this. So in the direction that the other mass is being attracted, they radiate out equally. The field lines never cross. And electric fields are the same. Field lines, magnetic fields, any field, the lines never cross. So it's headed in towards the center of the more massive object. Oh, here's a nice little diagram. This shows you how gravity actually varies a little. It's not in meters a second, it's in a special unit. Milligauss. I don't remember what a gal is, but it's small, tiny variations. Right, so if we want to measure the field strength, we are actually working the gravitational field strength. That's the acceleration due to gravity. That's just another way of saying that. So G equals Fg divided by m. So the gravitational field strength is the net force per unit of mass, and it works out to be the same as the acceleration due to gravity. All right, and it can be worked out here using that gravitational constant again, and the big mass divided by the radius squared. Right, so you can work out the gravitational field strength at a point 10,000 kilometres above the Earth's centre, or at the Earth's surface. It's just this formula. That's a constant. That's the mass of the Earth, and that's the radius squared. So that's gravitational field strength, small g. These other things are interesting, but not vital to anything. And that's the end of that chapter.